Section 2.4 is looking at some applications involving exponential functions. So where it says exponential functions as models, so basically applications. So we're going to look at specifically exponential growth and exponential decay, so when it's decreasing. And then we're going to kind of develop the equation for what we're going to look at ourselves here, I think with kind of a logical example. So it says, suppose that the population of a certain type of fish in a lake is currently 100 and is projected to grow by 2% each year. All right, so let's say it's year one here, and I didn't want it quite that. Okay, here we go. So suppose it's year one, and the starting population is again 100. So our growth is going to be 2%. So in this first year, we are going to grow by 2% of that, so multiplied by that 100. So that, of course, is going to give us 2. And so we're going to end up with a new population. So this 0.02 times 100, that is 2. And so our new population is going to be this 100 plus the 2. So we're taking our starting population, adding our growth, and that's going to be our new population. So we end at 102. All right, so leave a gap because we're going to fill in something in between here. Then that means in year 2, we're now starting at 102. Our growth is going to be 2%, so 0.02 times that now 102. So this comes out to be, if you compute that, this is 2.04. So if we add the growth to where we started, we would now be at 104.04. And so this is going to continue. But here's what I want you to observe here. So as I'm adding up, these first two values in order to get to this last value, let's kind of observe something here. In these first two terms on year one, I have a 100 in, let's say, both terms. So I could think about factoring out that 100. And so this would be 100 times 1, because I factored it out from the first term, plus 0.02 would be left in the second term. And so that is another way to think about how we're getting to that new value here. So again, kind of the same thing, but that is another way to kind of show that we get to that end result there. Okay, now if we look at the next line, very similarly here, if we look in both terms, I now have in the first term, I have 102, and in the second term, I have a 102. So I could factor out that 102. So if I factor out 102, it would be times the quantity of 1 plus 0.02. And again, that's just another way to kind of think about getting to that end result. Now, the 102 though, let's think about that. This 102, that was what was the new population up here at the end of, so there's 102 up here as well. And that was equal to this entire, from the first step, how did we compute 102? That 102 came from that 100 times 1 plus 0.02. So from that work that we have up above, so from, I'll call it asterisk here. So from asterisk, that was how we computed that 102. So again, this is a little bit, you don't have to know like where this came from, but I want you to see that it's just not all that super complicated. So at this point, I have 1 plus 0.02 times 1 plus 0.02. So that's 1 plus 0.02 squared. So that is now another way to think about how to get to that result. All right, so let's look at, I really want to highlight then these that we just came up with here. All right, so in the first one, it was this 100 times 1 plus 0.02 to the first. That's how we got to the end result. In the second one, we have shown it is 100 plus 1 times 1 plus 0.02 to the second. That's how we got to the, again, final population there. So as we start to observe here, I can even go back to that first one and think about putting in an implied power of 1. If we just look at what the input year is, so in this case 1 or in this case 2, that is what is going up in this exponent, and that is how we're getting to the final result. So if we continue this pattern, which we're not going to, rest assured, if we continue this pattern, but here's what we're developing. We're developing here that for any n that I have, that if I follow this pattern that I've developed of 100 times 1 plus, well, in fact, let's put this, let me erase this from here. For any n, in order to get to this final result, I can use this pattern of 100 times 1 plus 0.02 raised to that nth power. So if I wanted to jump ahead and figure out, I mean, this is fish. It seems weird to have a decimal amount of fish. I should change this to money or something, or some chemical substance that would make sense to have a decimal quantity. But this is the formula, the pattern we were developing here. So with that, a little bit of motivation for you for the formula. So this is our formula for exponential growth and decay. So in order to get to the y, the output, and it could be called p for the population, it could be called f of x, it could be called a lot of things. But that 100, so what was this 100? That was the initial population that we started with. So we are just going to call that A, where A is going to be, again, the initial quantity. Could be a population, it could be an amount of a chemical substance. So it's the initial quantity. And then we have 1, and depending on if we have growth here, so it is addition. So in a situation where you're going to have exponential growth, for growth, it's going to be addition. If you have an exponential decay situation, you are going to have subtraction. So exponential decay, is going to be the subtraction. So you have to kind of read the problem, figure out what you have, of course. And then, so that's the 1 plus, so we can see all that. And then what was this 0.02? Well, the 0.02, that was that growth rate. So we are going to call that R. So R is going to equal, this is that, I'll say, growth, or it could be decay, depending on the problem. And it's the percentage, but put in its decimal form. So it's the growth rate. So it's that growth or decay, percentage, put in its decimal form. And then we will raise that to the nth, or to probably in general, we will have that to the x power. And so x is going to be your input variable, or it could be n, or it could be anything. So this is one form in terms of thinking about our exponential growth decay model. Now, another form of this that you will see, and maybe even in your homework, is sometimes they like to actually tell the reader, let's not leave this as 1 plus 0.02. Like, just add it or subtract it if there's a problem. Make it 1.02 or make it whatever that would be. And so when we do that, what we get is they will refer to that actual sum or difference as A, and then the 1 plus or minus R, that is going to then be a variable B. So if you see that, then your B is just whatever that 1 plus or minus R is, just simplified. So that you're going to see, as a matter of fact, I think that your homework often will ask you to write out an exponential equation in that form. And so, that's basically it. Be prepared though, it could be in a different variable. Like, we could talk about, instead of the output variable being y, maybe we talk about p for a population of something. So they could call it p. They don't have to call it y. They could call it f of x. And similarly, they could call the input variable, another really common input variable here is t for time. So a lot of these problems are looking at, what's happening over time. So a lot of times they use a variable of t. So there's a lot of different ways to express it, but this is our equation, our exponential growth decay model. Okay, let's look at one example, and then we'll come back and look at the others next time. So as we look at this one, it says a culture of bacteria initially contains. All right, so that means, so first let me, in case okay. So initially contains 2,000 bacteria. So this tells me that my value of A, that constant, that initial quantity is 2,000. Okay, it's growing by 200% each hour. So this is going to allow me to figure out what my R is. So first of all, the growth is going to tell me addition. So let's just kind of note that for later. But the R in this case then, it's 200% in its percent form. So as I put it in its decimal form, decimal 2 places to the left, I know it looks kind of weird, but it's just 2. So that's the R in this case. So my exponential model, if you're asked to determine that, would be y equals, and so the first thing I'm going to sub in here is going to be my A. So the value of the A, and so the A is the initial quantity. So in these equations, the A is the initial quantity. So the first constant here that's going to go in is going to be that 2,000. So 2,000 is the initial quantity. And then whether or not I'm asked it in terms of like a 1 plus or minus R or the B, if I need the B, I have to figure out the B by doing 1 plus or minus R. So we start with the 1. This is growth. So in the growth situation, that is when we have that addition. Now the R in this case. All right, so our R, so the R is that growth or decay percent in decimal form. So that is that guy right there. So in this case, in its decimal form, looks a little weird, but it's just simply 2. And then that is going to be raised to the whatever I want to use. It's kind of my choice for my input variable. So to the x power, or n or t or whatever. So if I'm asked for in the form of a b to the x or a b to the t, it would be 2,003 to the x. So in this case, that whole quantity that would represent the b. All right, so that is my completed model, and now I can answer any question that they give me with respect to that model. Again, it could be if they ask you to use the variables P, maybe for the population of the bacteria or something. So there's just a lot of different variables that are going to just be really dependent on, the book or something like that. And so if you wanted to, you can use the parentheses. If you just want to use a dot, you could use that as well. That would imply the multiplication. So, just all depends on the variables that you're using. In any case, we need to find the amount of bacteria in 4 hours. So that is my input variable. And so I'm going to have 2,000 times 3 to the, and in my input variable there, 4. So of course the 3 to the 4th, that we can compute, that's just 81. And then the 81 times the 2,000, that's going to be 162,000 bacteria. Okay, so that's how our exponential growth decay, in this case growth, model works. So we'll look at some more next time.